Yeah. So if we're graphing position versus potential, what would a stable equilibrium look like on the graph? You can also consider this graph. Well, yes. I mean, there was always concavity.
Wait, can you repeat the question?
What would a place of stable equilibrium look like on a potential versus position curve?
Just do that and go back.
What?
Just go back.
Right, so if you push it in, well, that's what stable equilibrium means. If you push it a little bit, there will be a force exerting back. So what does the graph look like? Was this a point of stable or unstable equilibrium? This was stable, because if you push a little bit, there's a force back the other direction. What feature of the graph is that? This is a minimum. A maximum, if you have a maximum on a graph, this point is a point of equilibrium. If you go this way, what's the slope? Well, the slope is negative, which means the force is in the positive direction, which would push it farther away from equilibrium. So a point of unstable equilibrium is a local maximum. So stable equilibrium is a local min. Unstable equilibrium is a local max. And what do you think neutral equilibrium would look like? What kind of line? That is redundant. What does that mean? What does it mean when the line is like this?
Horizontal line.
Horizontal line. Yes. Child. Goodness. Right. You can think of, when you're thinking about equilibrium, you can think of a potential energy curve as being like a set of frictionless hills. So like if you put a mass here, it would just sit there. If you push a little bit to the side, well, it would roll back down. If you're up here, it's at equilibrium, you push a little bit to the side, it would roll away. So in that sense, it's kind of like frictionless hill. But remember, it's not necessarily talking about hills. Like this isn't a map of gravitational potential energy versus position necessarily. Yeah. So which of these points are points of stable equilibrium? X naught. X2. What about unstable? Right. Are there any points of neutral equilibrium? No, it looks like you're probably getting close to neutral equilibrium as x gets really big, but an asymptote, it'll never have a slope of 0, so not quite. It's close to being neutral equilibrium, but not quite. Now let's think about this. If I release an object at this point, call it point A, what direction will it move initially? Oh, I have to mirror. What direction will it move initially? Down. No. There's no down here. This is potential, not position. So right. To the right is correct. So if I release it at this x value, it will move to the right. Remember, this isn't actually a hill. So it doesn't go down, it goes to a lower potential energy, which is to the right. Actually, that's another way of thinking about it. Like objects always tend to move to a lower potential energy. That's kind of the same idea as figuring out the slope and getting the force. Objects tend to move to the lowest potential energy they can. All other things, being equal. So if I got this here and I let it go, what's it going to do? Well, it moves down to the lowest potential energy it can. Yeah. Anyway, so if I go here, it'll go to the right. It'll accelerate to the right. And then, how far will it go? It'll pass x naught, so it'll accelerate until it reaches x naught. After it passes x naught, what'll it do? It'll slow down, slow down. Will it make it to x1?
Yeah. How do you know?
How do you know?
You
You do
don't know.
know.
You do know? I do know. The hill is less steep and it's less tall.
The steepness doesn't matter.
It's
But what matters is this is less tall. It's a lower energy. So this has some amount of energy. So as it moves, it can move to a point of equal energy.
So it can keep going until.
So it'll go speed up, speed up, speed up, slow down, slow down, slow down, speed up, speed up, speed up, slow down, slow down, slow down, slow down, boom.
Oh, that's so cool. That's weird.
And it'll reach this point, point B. Those are called turning points, because the object would turn. And if nothing else, if the system wasn't losing energy for any reason, it would just go back and forth between those 2 points forever. But of course, in real life, we know there's always energy loss to something. Yeah. What in the world? We've gone too fast. Do 21. Tehan declares a thumb war. And for A also, just to say what kind of equilibrium they are. So Alberta, what approximately are the x values of the equilibrium points?
For stable, I said 10 meters and 22 meters. And then for unstable, I said around 16 meters. And then neutral, I said starting from 32.
From where?
32.
Mm-hmm. Sure. Well, actually, I guess I should technically say 32 to 50, because we don't know anything about what happens after the edge of the graph. So if I release the object at x equals 2, what's it going to do, Ian Chung? Mm-hmm.
And then slow down and speed up again.
And where?
13.
Mm-hmm.
And then slow down and then speed up.
What was the last speeding up?
Speeding up.
Oh, yeah.
21.
Uh-huh. And how far will it get?
Pretty far.
Mm-hmm. It's going to keep going at least until 50, right? So Move to the right. You know, speed up, slow down, speed up, slow down. Until 50 meters, at least. We don't know what happens after that. Yeah. Because it has enough energy. Each of these is 2, right? 2, 4, 6, 8. So we've got about 5 joules of energy at that point, and that's more than the level of this flat part over there.